This lesson will serve as a review of all of the concepts covered in week 9, which were precipitation reactions, the definitions associated with acids and bases, acid-base neutralization reaction, and then finally we introduced oxidation and reduction reactions and talked about rules for developing oxidation numbers. Precipitation reactions occur in aqueous solution due to the insolubility of one product. In order to predict whether a precipitation will form, when you mix together two aqueous solutions containing ions, you need to know the potential insolubility products that might form. We can predict which product will precipitate out of solution based on our solubility rules. Now, let's suppose that we are working in a laboratory and we mix together two aqueous solutions containing the ionic compounds magnesium chloride and silver nitrate. We can write the potential reaction as magnesium chloride plus silver nitrate. And this reaction has the form of an exchange reaction, or it's sometimes called a metathesis reaction. And this is one in which a reaction occurs between compounds that are written as a molecular equation, but it appears that they almost involve an exchange of parts between the two reactants. It's almost like an exchange of partners during a line dance. So if we exchange the anions between magnesium chloride and silver nitrate, we can get the products silver chloride and magnesium nitrate. And this is the balanced chemical equation for mixing together magnesium chloride and silver nitrate, both of which are aqueous solutions. So if the potential products for mixing together magnesium chloride and silver nitrate are magnesium nitrate and silver chloride, based on the solubility rules, we know that chlorides are generally water soluble, with the exception being silver chloride. Thus, we can conclude that silver chloride is not water soluble. Nitrates, on the other hand, are water soluble. This allows us to attach the phase labels and write out our entire molecular equation based on our solubility rules. So we know magnesium chloride will be aqueous. Silver nitrate will also be aqueous. Silver chloride will be a solid and will precipitate out of solution. Magnesium nitrate will also be aqueous. So this reaction predicts that the formation of silver chloride is an insoluble compound, and this compound will thus precipitate out of solution. If we go through our net ionic equation and we cancel out all of the spectator ions, which are just the ions that appear on the left-hand side of the equation and the right-hand side of the equation, which are magnesium and nitrate, we can collect our terms and obtain the net ionic equation, which is equal to 2Cl minus plus 2Ag1 plus yields 2AgCl, which is silver chloride, which is a solid precipitate. So remember that the net ionic equation represents the essential reaction that occurs. Silver and chloride ions combine together in aqueous solution to form this insoluble solid, which is silver chloride. Thus, we may conclude that any time silver and chloride ions are found in solution together, the precipitate will be silver chloride. Let's move on now to the definitions associated with acids and bases. When Arrhenius was developing his ionic theory of solutions, he also developed some classic definitions of acids and bases. Arrhenius defined an acid as a substance that produces hydrogen ions, which are H+, when it is dissolved into water. A good example of an acid is HCl, which is a molecular substance that dissolves into water to yield H+ and Cl- ions. It's given by this equation here. HCl dissolved in water breaks apart into H+ and Cl- ions. Now, according to Arrhenius, a base is a substance that when it's dissolved into water will produce hydroxide ions, OH-. According to Arrhenius, sodium hydroxide would be a good definition of a base. NaOH dissolved into water yields Na+ and OH-. On the other hand, Bronsted and Lowry defined an acid as a substance that transfers a proton during the course of a chemical reaction. They defined a base as a substance that accepts a proton during a chemical reaction. Therefore, in the reaction involving ammonia and water, the water molecule would act as an acid because it donates a proton to ammonia, and ammonia would act as a base since it is the one that receives the proton. So the equation looks like this. Ammonia plus water. Water is donating this H+ ion to ammonia, and we get the products ammonium and OH-. The dissociation of hydrochloric acid in water is actually a proton transfer reaction. Although the equation that we use for the Arrhenius definition doesn't really spell this out. This was the equation that we wrote when we were talking about the Arrhenius definition, which just says an acid is a substance that increases hydrogen ions when in solution. So if we rewrite the preceding reaction for the dissociation of hydrochloric acid like this, HCl plus H2O liquid yields hydronium H3O plus Cl-. This expression is more indicative of what's actually taking place at the molecular level. HCl is the proton donor, and H2O is the proton acceptor in this scenario. Now, there are a couple different ways in which we can categorize acids and bases. We can categorize them as either strong or weak. Now, acid and base strength is not the same as concentration. It refers to the extent in which the substance will ionize when it is placed in solution. A strong acid is one in which completely dissociates when it is placed into water. It is also a strong electrolyte. Nitric acid is a good example of a strong acid. When you add nitric acid to water, it completely or nearly completely ionizes and produces a strong electrolyte solution. If we contrast that to a weak acid is one in which will only partially dissociate when placed in solution. Hydrocyanic acid is a good example of a weak acid because it only partially dissociates when you place it in solution, and it will produce a small number of ions. Subsequently, it is also a weak electrolyte. A strong base is one that is present in solution almost entirely as ions. One of these ions is the hydroxide ion, OH-. A strong base is also a strong electrolyte. Sodium hydroxide is a good example of a strong base. NaOH, when placed in solution, yields sodium ions and hydroxide ions. Hydroxide compounds formed with alkali, which are group 1 or 1A, In alkaline, group 2 or 2A metals, with the exception of beryllium, are strong bases. If you contrast that to a weak base is one that only partially ionizes when placed in water. Ammonia is a good example of a weak base, and it subsequently is also a weak electrolyte. Neutralization reactions. An interesting property between acids and bases is that when they react with each other, they can actually neutralize each other out. We define a neutralization reaction as one in which an acid and a base react. The results are an ionic compound and possibly water. The ionic compound is a product of the reaction. This is called a salt. In general, an acid-base reaction looks like this. An acid plus a base yields a salt and water. Take, for example, when hydrochloric solution is mixed with a solution containing sodium hydroxide, the following reaction will take place. HCl, which is aqueous because it is a strong electrolyte, plus sodium hydroxide, which is also aqueous, yields sodium chloride, which is a salt, also an aqueous compound, plus H2O liquid. So this expression is the molecular equation for what takes place when you combine a solution containing HCl with another solution containing NaOH. HCl and NaOH are both electrolytes, which allows us to write them in their ionic form as H plus Cl minus plus Na plus OH minus yields Na plus Cl minus plus H2O. Now, if we cancel out the spectator ions, which are sodium and chlorine, we can obtain the overall net ionic equation, which is H plus H2O yields H2O liquid. This is the expression we get right here. So essentially what is occurring is you've got H plus coming together with OH minus to yield H2O liquid, which is water. And water is a very stable molecule. So we can say that really in this scenario, H2O is the driving force of the reaction, since everything tends to want to go towards a more stable state, and water is a very stable compound. There are certain salts, such as carbonates, sulfites, and sulfides, that when reacted with an acid form a gaseous product. Let's consider the reaction of sodium carbonate with hydrochloric acid. The reaction is given by the following molecular expression. Sodium carbonate plus 2HCl yields NaCl plus H2O plus CO2 gas. Now, it is useful to consider the reaction of sodium carbonate with hydrochloric acid as an exchange or metathesis reaction, since in this case, we are exchanging the carbonate ion with the chlorine ion to obtain sodium chloride and carbonic acid. Now, this product here, carbonic acid, is very unstable. This compound decomposes into water and carbon dioxide. So, the result of the combination of sodium carbonate and HCl is shown here with the following molecular expression, where carbonic acid has decomposed into water and carbon dioxide gas. If we write our expression in net ionic form and cancel out the ions that appear on both sides of the equation, which are sodium and chlorine, we can obtain the net ionic expression for a combination of sodium carbonate and hydrochloric acid, as carbonate plus 2H plus yields H2O liquid and CO2 gas. Now sulfites behave similarly to carbonates, and sulfides react with acids to form hydrogen sulfide gas. And these reactions can also be viewed as simple exchange reactions. For instance, sodium sulfite plus hydrochloric acid yields sodium chloride H2O and sulfur dioxide gas, because this one is similar to the carbonate reactions. Sodium sulfide, on the other hand, when added to sulfuric acid, yields sodium sulfate plus hydrogen sulfide gas. If we characterize acid-base reactions as proton transfer reactions, we can characterize oxidation-reduction reactions as electron transfer reactions. We can also simply call these redox reactions. Oxidation-reduction reactions are very important reactions that we encounter nearly every second of our lives. Everything from using food as energy, to burning fuels for energy, or harnessing the cleaning power of household bleach. All of these reactions involve oxidation and reduction reactions. Now, many of these types of reactions occur in solution. However, these types of reactions can be difficult to understand with minimal exposure to oxidation reduction reactions. So the first type that we looked at were non-aqueous redox reactions. These are very simple. So let's look at the formation of magnesium oxide, which is a solid, from the constituents magnesium and oxygen gas. If we take a better look at magnesium oxide, we see that it is an ionic compound that is composed of Mg2+, which is a group 2A element, and O2-, which is a group 6A element. Now recall that one can determine an element's charge based off its position on the periodic table. If you don't recall this, you had better review. In reaction involving magnesium and oxygen, magnesium transfers 2 electrons and oxygen gains 2 electrons. Thus, we can think of this reaction as occurring in 2 steps. One in which magnesium atoms lose 4 electrons, 2 magnesium atoms, and one where oxygen gas will gain 4 electrons. So the 2 half reactions look like this. 2Mg yields 2Mg plus 4 electrons. O2 plus 4 electrons yields 2 O2 minus. So the half reactions explicitly show what happens to the electrons during oxidation-reduction reaction. Now if we add these 2 half reactions together, we get the overall reaction as 2Mg plus O2 plus 4 electrons yields 2Mg2 plus 4 electrons yields 2 O2 minus. The electrons appear on both sides of the equation, so we can cancel them out. And we obtain the expression 2 magnesium plus O2 yields 2 Mg2 plus 2 O2 minus. Now, we know that magnesium and oxygen are going to come together to form our desired compound, which is our solid magnesium oxide. So we can write the final expression as this. The term oxidation reaction actually refers to the half reaction taking place, which involves a loss of electrons. The reduction reaction is the half reaction that involves the gain of electrons. Now, in the formation of magnesium oxide, we would say that magnesium is being oxidized since it is donating electrons to oxygen. Therefore, magnesium is acting as the reducing agent by donating electrons to oxygen, And oxygen is acting as the oxidizing agent by removing or accepting the electrons that magnesium is donating. The definitions of oxidation and reduction in terms of loss and gain of electrons accurately describe what is taking place in the formation of ionic compounds such as magnesium oxide, which literally involves the transfer and acceptance of electrons. However, these definitions do not accurately describe what is taking place during the formation of a molecular compound, such as hydrogen chloride or sulfur dioxide. Since HCl and SO2 are both molecular compounds, no electron transfer takes place during the formation of these compounds. Nevertheless, chemists still find it convenient to assign oxidation states to these compounds and treat the reactions as redox reactions, since experiments have actually shown that a partial electron transfer does in fact take place in the formation of a molecular compound. We keep track of the electrons during the course of a reaction by assigning oxidation numbers. An atom's oxidation number is also called its oxidation state. And this number signifies the charge the atom or molecule would have had an actual electron transfer taken place during the course of a chemical reaction. Thus, we can rewrite our equations as H2 gas plus Cl2 gas yields 2H plus Cl minus, and S plus O2 yields S positive 4, O2 minus 2. And these numbers above indicate the oxidation number. Now, in both reactions, there is no net charge on the atoms. Therefore, their oxidation number must be equal to 0. The product molecules, it is assumed that a complete electron transfer has taken place. Thus, atoms have either gained or lost electrons. And the oxidation number is therefore a reflection of the electron transfer that has taken place. So we see for HCl, positive 1 plus negative 1 is equal to 0. So it's a neutral compound. Sulfur dioxide, positive 4 plus 2 times negative 2 is also 0 because it is also a neutral compound. We also developed some rules associated with determining the oxidation number associated with a given atom. The first one being that alkali and alkaline metals, the oxidation numbers are generally positive 1 and positive 2 respectively. Elements, the oxidation number of an atom that is in its elemental form will be equal to 0. Monatomic ions, the oxidation number of a monatomic ion will be equal to its charge. Oxygen generally has an oxidation number of negative 2, except in instances of peroxide compounds. Hydrogen, generally positive 1, except when it is a binary compound with a metal, it will have an oxidation number of negative 1. Halogens generally have oxidation numbers of negative 1, fluorine with no exceptions, but chlorine, bromine, and iodine will have oxidation numbers different than negative 1 if they are in a binary compound with an halogen above it on the periodic table. Compounds and ions, the sum of the oxidation numbers for a neutral compound will be equal to 0. The sum of the oxidation numbers for a polyatomic ion is equal to the ion's net charge. To sum up, precipitation reactions occur in aqueous solution due to the insolubility of one product. In order to predict whether a precipitation reaction will form when you mix together two aqueous solutions containing ionic compounds, you will need to know the potential products that might form that could be insoluble. We can make predictions on solubility of ionic compounds in water based on the solubility rules. If there is a potential for two of the ions in aqueous solution to form an insoluble product, we predict that this product will precipitate out of solution to the bottom of the solution. Acids and bases are important electrolytes, and we looked at two different definitions, the Arrhenius definition and the Bronsted and Lowry definition. The Arrhenius definition is more based around aqueous solution, whereas the Bronsted and Lowry gives us more of an idea of what's taking place at the molecular level. An interesting thing about acids and bases is that when they react, they neutralize each other out. And we define a neutralization reaction as one in which an acid and a base react, and generally an ionic compound and possibly some water are formed. There are some salts, like carbonates, sulfites, and sulfides, that when reacted with an acid will form a gaseous product. Acids and bases are interesting compounds and are a very large part of chemistry. Finally, we introduced oxidation and reduction reactions. In oxidation reduction reactions, or simply redox reactions, are important reactions we encounter every second of our lives, nearly. These types of reactions literally involve the transfer of electrons between elements. And you can determine an element's oxidation number by using both a combination of the rules we developed and its position on the periodic table. Moving forward, we are going to spend some more time covering oxidation and reduction reactions. Then we will move on to calculations involving solutions.